Welcome to this lecture on using catalogs of physical effects as an inventive toolbox for engineering innovation. Imagine a catalog where each engineering function can be achieved through multiple physical effects, much like a periodic table of inventive solutions. Let us begin by understanding the function effect matrix, a systematic approach to inventive problem solving. Every engineering system performs functions such as clamping, mixing, switching, transporting, sensing, and actuating. Each function can be implemented using various physical effects including mechanical, electrical, magnetic, thermal, optical, and chemical phenomena. This matrix shows how different functions can be achieved through various effects. Green dots represent feasible combinations. Why do most designers default to mechanical solutions when many other physical effects are available? The answer lies in familiarity bias. Engineering education often emphasizes mechanical solutions, causing designers to miss opportunities in electromagnetics, fluidics, and other domains. Let us explore electrostatic clamping as our first example of unconventional effect utilization. Coulomb's law describes the electrostatic force between two charges. The force equals 1 over 4 pi epsilon 0 times charge 1 times charge 2 divided by distance squared. For parallel plates, the force can be expressed as 1/2 epsilon 0 times electric field squared times area. Let us perform an order of magnitude estimate for an electrostatic gripper in microrobotics. Assume an electric field of 1 million volts per meter and an area of 1 square millimeter. The resulting force is approximately 4.4 millinewtons, sufficient for microscale gripping without mechanical contact. This diagram shows electrostatic clamping where opposite charges create attractive forces without physical contact or moving parts. This principle is used in semiconductor wafer handling, where mechanical grippers would cause contamination. Next, we examine magnetic mixing using Lorentz forces to eliminate mechanical stirrers. The Lorentz force on a moving charge equals charge times velocity cross magnetic field. For a current-carrying conductor, force equals current times length times magnetic field times sine theta. Magnetic stirring uses rotating magnetic fields to drive ferromagnetic beads, eliminating mechanical contact with sensitive fluids. With a magnetic field of 0.1 Tesla, current of 100 milliamps, and length of 10 millimeters. The force is 100 micronewtons, sufficient for microfluidic mixing. This shows magnetic beads driven by a rotating magnetic field, creating fluid circulation without mechanical intrusion. This technique is critical in lab-on-chip devices and pharmaceutical mixing chambers where contamination must be avoided. Surface tension provides powerful forces at small scales for switching and actuation. The Laplace pressure equals surface tension times the sum of inverse principal radii of curvature. Water has a surface tension of approximately 72 millinewtons per meter. Consider a capillary valve in a microfluidic channel with radius 10 micrometers. For a spherical interface, Laplace pressure equals 2 gamma over radius. This gives 14.4 kilopascals of pressure, enabling passive valving without moving parts. A hydrophobic barrier creates a capillary stop where fluid halts due to surface tension, acting as a passive switch. This enables autonomous microfluidic circuits and point-of-care diagnostic devices that require no external valves. Phase transitions provide rapid transport mechanisms at microscales. The heat required for vaporization equals mass times latent heat of vaporization. Water has a latent heat of vaporization of 2.26 megajoules per kilogram. For a thermal bubble actuator used in inkjet printing, consider a 10 picoliter droplet. A volume of 10 picoliters corresponds to a mass of 10 to the negative 11 kilograms. The energy required is 22.6 microjoules, deliverable in microseconds with a microheater. A resistive heater creates a vapor bubble that explosively ejects a droplet, replacing complex mechanical pumps. This principle enables inkjet printers and DNA microarray spotting systems with no moving mechanical parts. What opportunities do designers miss by defaulting to mechanical solutions? They miss superior scalability to small sizes, faster response times, higher reliability with no wear, and easier integration with electronics. Optical effects offer switching without physical motion, through refractive index control. Snell's law states that n1 sine theta 1 equals n2 sine theta 2 at an interface. The critical angle for total internal reflection is the inverse sine of n2 over n1. In silicon photonics, temperature changes modulate the refractive index for routing light. Silicon's thermal optic coefficient is approximately 1.8 times 10 to the negative 4 per Kelvin. A temperature change of 50 Kelvin produces a refractive index change of 0.009. The resulting phase shift equals 2 pi over wavelength times delta n times length. A microheater changes the waveguide refractive index, switching light between output ports without mechanical motion. This enables high-speed optical switching in communications and solid-state LiDAR beam steering. Thermal expansion from Joule heating provides simple yet effective actuation. Joule heating power equals current squared times resistance, or voltage squared over resistance. Thermal expansion is given by delta L equals thermal expansion coefficient times length times temperature change. Consider a bimorph pH actuator made from two materials with different thermal expansion coefficients. Aluminum has an expansion coefficient of 23, silicon has 2.6, both times 10 to the negative 6 per Kelvin. At 5 volts across 100 ohms, power dissipation is 0.25 watts. This produces roughly 100 Kelvin temperature rise and 10 micrometer deflection in a 1 millimeter cantilever. The bimorph pH bends due to differential thermal expansion, creating mechanical motion from electrical input. Thermal actuators power MEMS mirrors for optical switching, microgrippers, and adaptive optic systems. Think of physical effects as elements in a periodic table, each with unique properties and combinations. Like chemical elements, physical effects can be selected, combined, and optimized for specific engineering functions. Just as chemists combine elements to create compounds, engineers can combine physical effects for innovative hybrid solutions. The shift to micro and nanoscales demanded rethinking of conventional mechanical approaches. MEMS accelerometers use capacitive sensing of a suspended proof mass, replacing bulky mechanical pendulums. AFM cantilevers detect atomic scale forces through laser deflection, impossible with mechanical gauges. Digital micro-mirror devices and projectors use electrostatic actuation of millions of tiny mirrors for image formation. Each mirror is electrostatically actuated, tilting to reflect light on or off for each pixel at kilohertz rates. At microscales, surface forces like electrostatics and surface tension dominate over body forces like gravity. The ratio of surface to volume forces scales inversely with characteristic length, making unconventional effects practical. Systematic exploration of the effect function space reveals unexpected solutions. Consider fluid pumping without mechanical valves or diaphragms. Electroosmotic flow applies an electric field parallel to charged channel walls, dragging fluid electrokinetically. The electroosmotic velocity equals negative epsilon times zeta potential times electric field over viscosity. With typical values of 10 kilovolts per meter field and 50 millivolt zeta potential, velocity reaches 1 millimeter per second. MHD pumping uses crossed electric and magnetic fields to generate body forces in conductive fluids. Acoustic streaming induces steady flow from nonlinear effects in oscillating ultrasonic fields. All three alternatives eliminate wear, reduce contamination, and require virtually no maintenance compared to mechanical pumps. Different physical effects offer vastly different energy and power densities. Electrostatic energy density reaches approximately 1 joule per cc. Piezoelectric materials store roughly 10 joules per cc. Magnetic systems achieve 100 joules per cubic centimeter with high field magnets. Power density varies dramatically across actuation methods. Thermal actuators manage 1 watt per cubic centimeter limited by heat dissipation. Piezoelectric actuators reach 100 watts per cubic centimeter in high-frequency operation. Effect selection must balance energy density, power density, response time, and integration constraints for each application. Advanced systems often combine multiple physical effects for enhanced functionality. MEMS switches couple joule heating, thermal expansion, and mechanical contact in a single device. Magneto-optic modulators use magnetic fields to rotate polarization, controlling light transmission. The Faraday rotation angle equals Verdet constant times magnetic field times propagation length. Energy flows through multiple domains in coupled systems, enabling functionality impossible with single-domain solutions. Modern, multiphysics simulation tools allow designers to optimize these complex, coupled systems. A systematic methodology leverages effect catalogs for inventive engineering design. Begin by abstracting the desired function from any preconceived implementation, focusing on input-output relationships. Search the effects catalog for all physical phenomena capable of providing the required function. Perform quick order-of-magnitude calculations to assess feasibility of each candidate effect. Evaluate how well each effect scales to required dimensions and integrates with system constraints. Build prototypes of the most promising candidates, and iterate toward optimal implementation. This systematic flow from function to implementation reduces design fixation and expands solution space exploration. Effect-based design has revolutionized multiple industries through unexpected solutions. Electroporation uses electric pulses to open cell membranes for drug delivery, eliminating needle injection trauma. E-ink displays use electrophoretic pigment migration, enabling paper-like viewing without backlighting. Thermoelectric coolers based on Peltier effect eliminate mechanical compressors in compact refrigeration. Peltier cooling rate equals Peltier coefficient times current times temperature. Selective laser sintering builds parts through thermal fusion, eliminating subtractive machining for rapid prototyping. Each breakthrough emerged from reconsidering fundamental functions without bias toward conventional mechanisms. Despite advantages, unconventional effects face adoption barriers that must be addressed. Engineering education traditionally emphasizes mechanical and structural analysis over unconventional effects. Solution requires integrating multi-domain design courses early, building familiarity with diverse effects. Many designers lack access to multi-physics simulation tools needed for coupled effect analysis. Creating accessible effect databases with built-in scaling calculators lowers the barrier to exploration. Industrial risk aversion favors proven mechanical solutions over unfamiliar physical effects. Building prototype libraries demonstrating successful implementations reduces perceived risk and builds confidence. Understanding how different effects scale with size reveals natural application domains. Gravitational forces scale with volume, proportional to length cubed. Electrostatic forces scale with area, proportional to length squared. Surface tension forces scale linearly with characteristic length. This scaling behavior explains why different physical effects naturally dominate at different size scales,